Hello again everyone. So in this video I'll be talking about vector subspaces. Alright, so essentially and very informally what a vector subspace is a special kind of subset of a vector space. A vector space. Okay, so again, remember how we usually represent our vector space. So a vector space is kind of like this space, right? So we'll call V our vector space. V is our vector space. Okay, and inside of it we have a subset. We have a subset of that vector space, which we'll call a subspace. Okay, so let's say this is a subspace. Okay, for a subset to be a subspace of a vector space, it needs to follow three specific conditions. Okay, so already the first thing that needs to happen is that for a set W to be a subspace, well, it can't just be a subspace, it needs to be a subspace of a vector space. So of a vector space. So you can't have a subspace alone, it needs to be a sub of something, hence the sub from subspace. So for a set W to be a subspace of a vector space, the first thing that needs to happen, this is even before we get to actual conditions, is W must be a subset, of my vector space V. So this was initially in red. Okay? And so the idea behind vector subspaces is that if something belongs to my subspace, I want it to have certain properties, certain conditions, where if you take an element, so I'll just give you the conditions informally. So say you take two elements U and V that are two vectors in this case of the set W, and also of the set V, because W is a subset of V. Well, for W to be a subspace, the first condition is that somewhere in the set you need to have a zero vector. So there must be a zero vector. The second thing is, if I have two vectors, I have the vector U and V in W, then if I have my vector addition, so my vector addition is just U plus V, that vector addition must also belong to W. And then if, suppose I take V and I scalar multiply it by a scalar C, so suppose C is a scalar, then if I scalar multiply V by C, then that scalar multiple should still be within my vector subspace W. Okay? So that's, loosely speaking, that's what it means for something to be a vector subspace. Let's do it a bit more formally, okay? So let's do it. So for a set W to be a subspace of a vector space, the first thing is that W must be a subset of V, and W must follow the following three conditions. Okay, so my first one is that the zero vector has to belong to my set W. In other words, W cannot be empty. So it needs to have something, and that something we've decided is the zero vector. The second thing is that suppose we take U and v, so two vectors u and v that belong to my subspace W, then if I do the vector addition, so if I do u plus v, then that vector addition will also belong to the subspace V. And this property actually has a name. It's called closure under, and we usually don't say it, but we mean vector addition. That is to say that it's closed under addition because if I take two elements, u and v and w, and I add them together, they won't jump out and go here. They'll stay inside my subspace W. Okay? And the last thing is that if u belongs to my subspace W and C is a scalar F, then CU, in other words, U scalar multiplied C, will also need to belong to W. And this is called the closure under scalar multiplication. So again, that is to say that if I take an element V and I scalar multiply it by C, then it won't end up somewhere here in my vector space V. Rather, it'll stay within. It'll stay closed. So it's like this box that's W closes in, sort of keeps all of its elements inside. That's sort of the gist of it. Okay? So let me give you a quick example. So we won't prove that this is a vector subspace yet. I'll just tell you that it's a vector subspace, and we're going to look at some of the properties of it. Okay, so suppose W is a subspace of R3, okay? And I define W as W is equal to, so it's the 3-tuple set, right? Such that the first component is equal to the second component plus the third component. So if you get an arbitrary, so something that seems very made up, it'll usually look like this. We'll tell you that W is a subspace of a vector space. So we know that R3 is a vector space. So we know that this is a vector space because, remember why? Because it meets all 8 axioms. So it meets all 8 axioms 1 through 8 because this is just a specific case for Rn, right? So in this case, n is actually equal to 3. That's why we have 1, 2, 3 components. Okay? So, but I'm already telling you that it's a subspace. I'm not asking you to prove it. So now, let's just look at some of the properties of this subspace. So, suppose, well, let's not go with suppose. Let's just take 2 elements in W. So 2 elements in W, that's going to be, say, 0, 1, minus 1, and 2, 1, 1. Okay? And the reason why I know, so why are these in V? Why are these in, not V, actually W, even though they are also in V, is because if you take the second component and you add it, so if you take the second component, add it to the third, right, this addition will actually give you the first component. Similarly here, if you add these two together, that's 2, and then the 2 is actually your first component. So let's look at some of the, well, the 2 most often confused and hard conditions for a subspace, because 0 belonging to W is that's pretty trivial. The ones that bother people the most are 2 and 3. Actually, more 2 than 3, but we'll look at all of them. So if this is U and this is V, then I know that because it's a subspace, U plus V should belong to W. But let's check that. So let's check whether U plus V belongs to W. So does it? Let's see. Okay, so if I do u plus v, well, that's equal to 0, 1, minus 1, plus 2, 1, 1. And that's equal to 2, so now I'm just adding the components, so the first component with the first component, and so on. So 1, that looked like a 1. So then in my second component it's 2, and then minus 1 plus 1 is 0. Okay? Well, so does this belong to W? Well, you might be like, okay, well, I get this vector, but like, what does it really have to do with my subspace? Well, think back at the actual definition of W. The definition of W has one condition. It's a subset, it's actually a subset of R3, and it has the particularity that the first component is equal to the sum of the next two components. So is that the case? So let's check. So basically how you would check if this belongs to W is you would check the condition. So check the condition. Okay, so my first component x1 is 2, and my second component is 2, right? So that's my first component, that's my second. And my third component is 0. Now, is x1 equal to x2 plus x3? Well, it sure is. 2 is equal to 2 plus 0, which is actually just 2. Okay, so we've actually checked, we've verified that the sum of two particular vectors in W, that sum, that vector addition, also belongs to W. Okay? I'll show how to do the proof later on, but this is just to sort of getting used to the idea behind these subspaces. Now let's also check the third condition. So check if closed under scalar multiplication. Okay, so let's check that. Okay, again, actually no, not again. Let's use a different vector just for fun. So let's say u is equal to, I don't know, let's do 2, 3, and, well, 5. It needs to be 5 or else it wouldn't be known. Okay, and let's pick a scalar c that's equal to 2. Okay, so I want to verify, so basically I'm trying to verify if c scalar multiplied u is also in W. Okay, well, let's see. So what we actually have to do, we have to do the scalar multiplication. So if we do c scalar multiplied u, then that's equal to 2 scalar multiplied 5, 3, 2. Okay, this is a pretty easy multiplication. So I just multiply each component, 5, 3, and 2 by 2. So 2 times 5 is 10, 2 times 3 is 6, 2 times 2 is 4. Okay, so let's check. Now, to see, so does this belong to W? That's the question. To see if it does belong to W, check the condition. Okay, so let's check the condition. Okay, so x1 is 10, x2 is 6, x4, not x4, x3 is 4. Now, does x1 belong to x2? No, not belong, sorry. Is x1 equal to x2 plus x3? Well, 10 is in fact equal to 6 plus 4. So yes, that is the case. The condition is met. And so this vector here, cu, actually belongs to W. Okay, so that was an introduction to vector subspaces. We'll do actual proofs for vector subspaces next.